I can repeat the question. Oh, yes.
Can you comment about the mission to share the solution with brain score benchmark?
Yeah, absolutely. I can repeat the question. Yeah. So the question was, how can I talk a little bit about how CAB relates to brain score? Thanks for your question. So brain score is a leaderboard that measures how well different vision algorithms perform in predicting primate neural data. So the target for explanation there is the result of neurophysiology experiments performed in primates, including humans as well, I think. And it's meant as a way of building consensus across the AI and neuroscience and cognitive science communities, for that matter, with respect to what the targets are and how close we are to achieving them. So CAB has a very it's quite inspired by projects like BrainScore. I think the goal is to bring a fair amount of discipline and a sense of, I suppose, team spirit to the study of these kinds of behaviors. So for neural data, BrainScore would be like a good tool for that. For these kinds of higher level cognitive phenomena, including physical understanding, exploration, natural communication, there are a variety of different data sets out there that you can use to train or evaluate various models. In parallel in cognitive science, there are a variety of what we call stimuli and experimental task paradigms, where you might test some of those behaviors, but not often in tandem and in parallel in such a way they can be directly and quantitatively compared to one another. So one key distinction is the focus on rich behaviors as opposed to neural data, but there's a quite close kinship with projects like BrainScore insofar as they're about organizing the community and rallying the community around particular benchmarks and putting in the elbow grease to build comprehensive enough ones that they would be convincing to the community as a whole. And I would say that unlike other recent work that has amassed large human data, so I'll mention that human behavioral data that accompanies the kinds of image sets we're used to working with in computer vision are also expensive, but worthwhile to collect if your goal is to build human level and human-like AI. And CAB is very much dedicated to putting resources towards collecting high quality human psychophysical data of that kind. And so really identifying a core suite of human behaviors that are natural for people to do, that are still difficult for current AI systems to perform, and that we also think are likely candidates to push AI forward, are good candidates for inclusion in CAB. That was a lengthy answer to a simple question. Any other questions? Yeah, sure.
Thanks for the great talk. I think you addressed this a bit in Physion 2.0, but I'm curious to what extent you think there may be biases in the data set that the model could pick up on, but a human can't. So at the very beginning, you showed like what I assumed to be a brick falling on a bowl, and then the bowl actually balances, and I almost felt fooled. And I'm curious, like, to what extent I made an assumption about the mass of that object that I think the model may have been able to make that I wasn't. I'm just curious, like, what extent you think that exists in the data?
Thank you. That's such a rich and interesting question. It's something that we're wrestling with an ongoing data set design, as you can imagine. So let me try to unpack that. So one piece of it is, are there priors that our human observers are bringing to the experiment that models aren't? Almost certainly, because people are trained, if you will, on a wide variety of different tasks, if you will, on much more diverse data. And they're actually they're generalizing to this set of toy objects in these settings. The models are trained however they're trained, and then basically adapted only for the purpose of evaluation. This is not intended to be a test suite, a training data set, but rather a test set to study transfer learning. And, you know, there's some interesting cases where there are aspects of human priors that are quite interesting and worth unpacking. For example, you can make inferences about materials, like based on the surface texture of certain materials, guesses about how heavy an object is or its density. In trying to control for that, we opted for mostly wood-based textures in this current release, but we're planning to introduce more diversity along that dimension in future releases, which could be disruptive for people, but also be an interesting way of studying visual adaptation on the part of people who can learn to infer the properties of objects after observing them interact with some. So one other aspect of Physion 2.0 that I didn't mention is that even if an object is surprisingly light or surprisingly heavy based on what you've inferred from its texture, you might see that it, it was knocked over really easily. And then so when you see it land against something else that you also think is really light, but it fails to move it, you may be less surprised. And so for those more extended kind of natural interactions over time, I'm really interested in how people build up from online observation a working hypothesis about these latent physical properties. They may not be entirely given away by knowing their label or other kind of abstract, semantic information that they have. There are, of course, other reasons why some of these videos might look a little bit weird. And if you download our test set, you'll find them. We've included a README with the file names for those videos already tagged. So there are some that we've been calling adversarial cases. They're ones that are so weird that our sample of human participants consistently got them wrong, and the physics in them looks really, really strange. So on the one hand, this could be a limitation of our simulator, which is something that involves like some engineering to work out until it approximates physical realism better. That's one tack you could take. Another tack that I think is very interesting from the perspective, if you're interested in, for example, continual learning, is that we, of course, generalize to new virtual worlds with different physics when we play video games and when we go to different environments, say underwater or into outer space. And there's a really deep question about how we, as primates who evolved to move around on the surface of the planet, have managed to adapt to a wide range of physical environments, including ones with unfamiliar kinds of physics. And I think asking those questions about generalization can also be a really, really interesting direction to go in thinking about what we would want, from more adaptive AI systems, not only saw the world the way that we do, but also learned to see the world the way that people do across the lifespan. Yes.
Hi, thank you for your talk. I was just interested in how what you think about how humans represent these 3D dynamics, because linking back to the scene graph from the last talk, I think it'll be really difficult for scene graphs to model these kind of deformation or liquid, like viscosity, etc. But also it would not really generalize if you're planning in image space, I would imagine. So what would you think is a good representation for humans to be able to plan or model future dynamics?
Thank you for your question. Right. So I mentioned briefly when describing Physion 2.0 that we plan to include additional readouts. So one readout that we've started with is the base binary judgment about contact. In the future, I think what we really want is a suite of different behavioral readouts that encompass physical scene understanding at multiple levels of abstraction. I actually don't think there's going to be one single way that humans represent 3D scene dynamics in all scenarios. There may be some that may be more core and computed automatically, even without conscious awareness. And those are good candidates, I think, for places to start. But and even for those problems, thinking about like object level abstractions as well as event-like abstractions could be really critical for capturing human level and human-like physical understanding and, you know, approximating the level of like the kinds of confusions that people have. But we also think that in addition to these more like quasi-linguistic descriptors of, well, we've already kind of imbued our OCP task with a little bit of semantics, right? We're like using kind of a particular kind of abstraction, if you will, that it can also be picked out by language, right? Namely, naming the occurrence of a particular event, right? And we think of those as being really important. They're important enough that they've been encoded into the way that we talk to each other. But there are also ways in which we move about the world and predict how objects behave and intersect objects that don't necessarily have easy, that we haven't necessarily baked into our vocabulary. So when you're like playing sports and you're thinking about all the various ways in which you can move a tennis racket, a lot of them are really hard to describe and much easier to show through demonstration. So another set of tasks that we think would be really powerful to augment this existing benchmark with is tasks that involve like online interception and more continuous kinds of prediction to accompany these somewhat more semantic kinds of readouts that we have started with anyway. And which ones are relevant may depend a lot on context, especially for people.
All right, thank you very much, Judith. One more round of applause, please.